Welcome to our introduction lesson to electromagnetic radiation. Over the next few lessons, we're going to be unpacking this very interesting and exciting branch of physics. And we're going to be having a look at how it has applications in so many different ways for our everyday lives. Everything from the song you heard on the radio to the cell phone call you made this morning, and even the x-rays done in the hospital near you are all examples of electromagnetic radiation at play. As part of this section, hopefully, you will also come to understand that not all electromagnetic radiation is super dangerous or is going to turn you into the Incredible Hulk. In fact, hopefully you'll realize that it's got many, many useful applications in our everyday lives. But before we begin, we must pose ourselves a simple question. Let's go to the board. Have you ever thought about how a reflection of your face in a mirror is always the perfect representation of your facial features? Have you ever considered why, when you stand in a very dark room, our reflection does not appear in the mirror at all? These are the kinds of questions that hopefully by the end of these lessons you'll be able to answer for yourself. Let's move on to our concept map. Obviously, as part of our investigation, we're going to be looking at the electro and magnetic aspects of electromagnetic radiation. But as part of that, we're going to be linking it to how electromagnetic radiation propagates from one place to another, and what different types of electromagnetic radiation we find in the spectrum of electromagnetic radiation. But before we get into any of that, we first need to understand electromagnetic radiation in a little bit more detail. To do that, we're going to start by examining how electromagnetic radiation can be said to behave like the waves we've already looked at as part of sound and mechanical waves, but also, and often more interestingly, how electromagnetic radiation can behave like a particle. And it is this dual nature that will form the basis of many of our interesting and unique questions for this section. Before we begin though, let's have a look at some key words to make sure we are familiar with them. The first word is medium. It's one you should be familiar with from your previous work in waves, and not one you confuse with the type of steak that you buy at your local Spur. The medium in physics is the substance through which a wave passes. It is the substance through which the energy is transferred. We also have the word energy down here, and that is because obviously all waves represent energy moving from one place to another. We need to remind ourselves that all waves have a frequency, which is a measurement of how often a particular event occurs per unit time. In the case of waves, it's how often a wave front passes a particular point in the medium per unit time. We also know that all waves travel through their mediums with a particular velocity, and this will form the basis of quite an interesting discussion on how fast electromagnetic radiation travels and how it's the fastest thing we've ever observed. Finally, you should be familiar with the idea of electromagnetic, in that all of the radiation in the electromagnetic spectrum is made up of two components, one electrical and one magnetic. So what is electromagnetic radiation? Well, electromagnetic radiation is different forms of energy. We get forms that are very high energy and can be quite potentially dangerous to us, and forms that are relatively low energy and pose almost no risk to us. We see electromagnetic radiation in all its different forms all over the place in our modern lives. We see it coming out of the light fixtures that we use to illuminate our homes. It's used by X-ray machines in hospitals to take a look inside people's bodies and see what's wrong. And as I mentioned at the beginning, it's used to transmit radio signals across our country so that you can hear your favorite song no matter where you are. As part of our investigation into electromagnetic radiation, we have to ask ourselves the questions: is electromagnetic radiation a wave or is it a particle? To better answer these questions, we need to unpack the properties of waves and particles and relate them to electromagnetic radiation to make a decision. For us to better understand the electromagnetic spectrum and radiation, we need to pose ourselves two important questions. Does electromagnetic radiation behave like a wave, or does it behave like a particle? This question and this dual nature of electromagnetic radiation forms the basis of a lot of scientific debate and will form the basis of a lot of the investigative work we'll be doing in this section. So what are the properties that both waves and particles share? Well, we already know that waves transfer energy through a medium, but particles can also transfer energy. Think about throwing a tennis ball. If you throw a tennis ball hard enough against a wall, you can hear the energy that it transfers in this form of sound, and if you had a very sensitive camera, you'd also be able to see that where the tennis ball hit the wall, there was a slight increase in temperature. That is, again, a transfer of the energy from the tennis ball as a particle through the medium that it's traveling to the wall at the end of its journey. The next property that waves and particles share is that the energy that they transfer always comes from a particular source. In the mechanical waves that we looked at earlier, like sound or waves on a string, the energy came either from your voice or from you shaking the string to create the pulse that traveled down it. In the case of a particle, like our example with the tennis ball, the energy comes from you, the person who throws it. So let's move on. In our understanding of waves, we've already looked at the wave equation. We already know that the wave equation is a means to calculate the velocity of a wave when we have its frequency. Let's go to the board for a bit more information. In the wave equation, as I said, we are able to calculate the velocity of a wave by taking the product of that wave's frequency and its wavelength. You should already know that the frequency of a wave is the number of times the wave passes a particular point per second. And the wavelength is the distance between any two consecutive points of a wave that are in phase. We often refer to a wavelength as the distance between two consecutive crests or two consecutive troughs. With the wave equation, as I said earlier, we already know that we can use it to calculate the velocity of a wave when we have its frequency and its wavelength. As we said earlier, frequency is simply how often an event associated with a wave occurs. In the case of the mechanical waves we've already looked at, the frequency is simply how often a wave front passes a particular point in the medium per unit time. We should already know that wavelength is simply the measure a measure of the distance between any two consecutive points on a wave that are in phase. We often say this could be from crest to consecutive crest, or even trough to consecutive trough. Now we need to take a look at some of the properties of waves we've already looked at and see if we can relate them to electromagnetic radiation. We already know that waves always move in straight lines. To picture this, think of again splashes in a pond or ripples in a pond. When you create a disturbance in the medium, the waves from that disturbance travel outwards in straight lines. The next property that we've already looked at for waves is this idea of reflection. We know that waves reflect, and we can see this in our everyday lives. If you ever speak into a room that is large and empty, and then hear your voice bouncing back off the walls in the form of an echo. That echo is the reflection of the sound waves back to your ears. We also know that waves are able to refract, which is the changing of their speed as they change mediums. This one's more challenging to picture in the real world, but a nice example of it is waves crashing or breaking on a beach. With waves on a beach, as the waves approach the shoreline, the shoreline rises, the water becomes less deep. This causes the water to slow down and results in that typical curling and crashing shape that we associate with waves. The next property of waves we've had a look at is that of diffraction. Diffraction is the process whereby waves can bend round an opening or through an opening and then spread out. This opening is often called an aperture in physics. A nice example of this is if there's ever been a large group of people making a lot of noise in a room. If that room has a single window that is open, you can usually hear all of the sounds inside the room, even if you aren't standing directly in front of the window. You could be above it, below it, quite some distance from it, and you'd still be able to hear the sound because the sound waves are diffracting through the opening that is the window. The last wave property that we've had a look at is that of interference. Interference is also not one that we see very commonly in our everyday lives, unless you know a little bit about the acoustics of music and playing it in a large venue like a hall or a concert venue. These large halls and concert venues are built in such a way that the sound waves constructively interfere at all the different places inside the hall to ensure that the sound sounds exactly as if you were standing right at the front of the stage, no matter where you are in the room. Now let's have a look at some of the properties of particles and try and relate them to the properties of waves we've already discussed. As you can see listed on the board, particles also travel in straight lines. They also are able to reflect. Again, think of our tennis ball example and how the tennis ball will only move in the direction of the force that's applied to it, and it will always bounce back off of an object that it collides with. But we also have observed that particles are capable of changing their speed when they move through different media. Remember, media is just the plural of medium, all right? So continuing with our tennis ball analogy, the tennis ball will quickly change speed if it hits a surface that is rougher or smoother, all right? Our tennis ball also has a mass, and that's how we are able to consider it a particle. And it is this mass that means it is able to collide with other objects. And the last property of particles we need to consider is that they are able to penetrate objects when they are projected with high amounts of energy. So, the last thing we need to do is ask ourselves a few more questions, like, is everything with these properties a wave? What happens if we can't see the properties with our eyes? And finally, the most important question for this lesson, is electromagnetic radiation a wave or a particle? Let's take a break, and then we can come back and find out. Welcome back from your short break. Let's continue with our investigation into the electromagnetic spectrum and electromagnetic radiation. We've already had a quick look at some of the properties of waves and particles, some of the properties that they share. Now it's time to relate them to the electromagnetic waves we've been talking about and see how these properties give rise to the different types of electromagnetic radiation we see in the world around us. Let's head to our concept map though to unpack. We've obviously already been looking at electromagnetic radiation, and as I said earlier, we have been examining how the properties of particles and waves. We've also examined how some particles and waves can share properties, and now our goal is to link them to this idea of electromagnetic radiation, as well as linking those ideas to how electromagnetic radiation propagates from one place to another. So we've been posed this question: is electromagnetic radiation a wave or is it a particle? This is a debate that has raged in the scientific community for many, many years and has sparked many papers and insights that have proved extremely valuable in our exploration of our world. These discoveries or insights into electromagnetic radiation have contributed in fields as far and as wide as medicine, technology, and even space travel. And for us to make the most of these questions, we need to delve deeper into the properties of electromagnetic radiation and see if we can relate them to what we already know about waves. So what are the origins of electromagnetic radiation? Where does it come from? Well, it being a wave, we can quite confidently say that it must originate from some kind of source. All right? And this source must provide the electromagnetic radiation with some kind of energy for it to be transmitted. We know that all waves are energy being transmitted. So what are some common examples of sources of electromagnetic radiation in our everyday lives? Well, the most important by far is the sun. Without the energy provided by the sun, there would be absolutely no life on Earth as we know it. It would all be very simple and require very small amounts of energy to survive. The sun is a massive source of electromagnetic radiation, and it doesn't only provide electromagnetic radiation in the visible light spectrum so that you and I can see each other on a sunny day. It also produces electromagnetic radiation that is in the radio wave part of the spectrum, and even the more dangerous X-ray and gamma rays can be produced by the sun. What about an example closer to home? Well, a common source of a wide range of electromagnetic radiation is lightning. Now, we usually associate lightning with a bright flash in the sky, followed by a thunderclap. That light that we see is in fact the visible light, or the visible part of the electromagnetic spectrum that the lightning is actually producing. But with the right equipment, you would be able to see that lightning also produces radio waves and even the slightly more energetic and dangerous X-rays. Now, in both of our examples, we haven't made any mention of a medium. Of course, in the case of lightning, the medium is simply the air of our planet. But what about the electromagnetic radiation coming from the sun? It's traveling through space. So what's going on there? Space is a vacuum, right? It's got nothing in it, or at least very, very little in it. So how does the electromagnetic radiation travel through it? Well, we're going to be looking at it in a bit more detail soon, but for now, we only need to know that electromagnetic radiation doesn't actually require a medium to travel through. One of the properties of electromagnetic radiation is that it can travel with or without a medium to pass through. This is what allows light from the sun, stars, distant planets, even distant galaxies to reach our eyes, even though it travels through the vacuum of space. Another property of electromagnetic radiation is that it occurs at a range of different frequencies. And these different frequencies are what give rise to all the different properties and types of electromagnetic radiation. We've mentioned quite a few types of electromagnetic radiation already. We've talked about radio waves, light, visible light, X-rays, and we've even mentioned the very dangerous gamma rays at the end of the spectrum. But what about all of these properties of waves that we were talking about earlier? Do electromagnetic waves obey the same rules? Do they have the same properties? We already said that waves move in straight lines and they are able to reflect off of surfaces that they come into contact with. Do we see this with electromagnetic radiation? We absolutely do. Take a look at this laser pointer being shone on a reflective surface. We can clearly see that the light from the laser pointer, light is a type of electromagnetic radiation, remember, is traveling in straight lines, both to the surface it reflects off of and away from it. Both of these lines are nice and straight. What about some of the other properties that we looked at for waves? What about the more exciting and complicated ones like refraction and diffraction and interference? Do we see those in electromagnetic radiation? We absolutely do. So let's have a look. We do in fact see that electromagnetic radiation is able to refract and diffract, and that it is also able to undergo interference, both constructive and deconstructive. A wonderful example of this is simply allowing light, white light, to shine through a soap bubble. In the image, we can clearly see along the top all the different colors that we associate with light. And those colors have been broken up from the white light. But notice also that along the side, we can see bands of dark and bright regions in the soap bubble. These are examples of interference. Where the bands are dark, the light is deconstructively interfering. Where the bands are bright, it's constructively interfering. What about the particle nature of electromagnetic radiation, though? We've been focused on the waves, so where does the particle aspect come in? Well, we already said that all particles have some mass. Does this mean that light has a mass? If I stand here in this room and hold my hand out, there are lights shining on it. Am I holding something with mass? It certainly doesn't feel like it. So what's going on here? If light is a particle and it has mass, doesn't that mean that it then should collide with objects or other particles as it travels through any particular medium? What about what happens when there isn't a medium? If we look at the physics of bigger objects, like, say, a cannonball or a wrecking ball, we know that collisions definitely involve the transfer of energy. We hear it in the sound that the collision makes, and we see it in the changing of the shape of the object that is collided with. Does this mean that light is able to collide with other particles? A really good question. It's one that's been the topic of quite a lot of scientific investigation. And it forms, and the idea that light can collide with particles forms the basis of a concept known as the photoelectric effect, a very famous phenomenon in physics that you'll learn quite a bit more about in grade 12. But for now, what is the photoelectric effect? The photoelectric effect is when delocalized electrons on the surface of a metal get ejected when an electromagnetic source or an electromagnetic wave of high enough energy hits the metal. So I'm going to try to draw a diagram to help you understand. If we have our metal, and on its surface there are delocalized electrons, in the photoelectric effect, when an electromagnetic wave of high enough energy strikes the metal, these surface electrons can be kicked off. And this is strong evidence for how electromagnetic radiation behaves like a particle. Now, from what we've seen, electromagnetic radiation seems to have a dual nature. There are some of its properties that are wave-like but don't apply to particles, and there are some properties that are particle-like but cannot be explained by waves. To solve this problem, we look at this nature in two separate ways. We look at all wave properties as waves and all particle properties as particles. The particles associated with electromagnetic radiation are called photons. They are little packets of energy, and they are said to have a frequency but no mass. That's enough for now, so I'll see you after a short break. Welcome back from that short little break. It's time now to delve deeper into electromagnetic radiation. We're now going to take a closer look at the wave equation and how it applies specifically to electromagnetic radiation. And later, we're going to have a look at how electromagnetic radiation propagates. So let's head to our concept map. We've been unpacking electromagnetic radiation. As before, we have looked at the properties that it exhibits like waves. We've looked at the properties of particles that it exhibits. It's now time to bring in this idea of how fast the wave is traveling and how it propagates through space. So let's have a look at the wave equation. In the wave equation, we already know that you can calculate the velocity of a wave in meters per second by taking the product of the frequency of the wave, which is measured in hertz, and its wavelength, which is measured in meters. But electromagnetic radiation is quite unique, and for that reason, we have to modify the wave equation so that it makes sense in terms of electromagnetic radiation. So how are we going to do that? Let's have a look. As I said, electromagnetic radiation is quite unique in terms of waves. In fact, it travels faster than anything else in the entire universe. In fact, we are pretty sure that the speed that electromagnetic radiation travels at is as fast as anything can go. Interestingly, and part of why electromagnetic radiation is so unique, is that the wave speed for electromagnetic radiation is the same as long as the electromagnetic radiation is passing through a vacuum. Therefore, all electromagnetic radiation, when passing through a vacuum, travels at the same speed. This speed is quite important, and so it receives its own symbol, c. c is equal to 3 times 10 to the power of 8 meters per second. c is a very important variable in physics, not just for waves. You may have encountered it even in one of the most famous physics equations ever, Einstein's own E equals mc squared. That c you see there is the exact same c that we are referring to, the speed of light. So how fast is that? I mean, it seems pretty big a number, right? it's got 8 zeros after that 3. I mean, think about it. When you're driving on the road in a suburban area, you're only doing 60 kilometers per hour. So how fast is light in comparison to that? Let's have a look. We've already said that c is the symbol for the speed of light. But if we convert it from meters per second to kilometers per second, we can see that it's a huge amount. 300,000 kilometers per second. Significantly faster than you would go on the highway even. Significantly faster than any of us will ever go. This is why you'll never see light traveling. It's just too fast. Have you ever noticed that when you turn on the light in your room, you never catch the light traveling across the room? The room is either dark or then instantly lit. The reason for this is that the speed of light is just way too fast for us to see. Our eyes are just not geared to be able to see the light or the wave moving through the air as it goes. So let's have a look at some questions to get our heads around the numbers associated with the speed of light. So our question here is, how long does it take for the sun's electromagnetic radiation to reach the Earth? To do this calculation, we have to A, know the speed of light, which we've been given, and B, we need to know just how far the sun is from the Earth. Now this number is quite big. It might surprise you. The sun is 150.38 million kilometers away from the Earth. So how long does it take this super fast light to reach us? So to begin, we need to list all of our variables. We have the speed, 3 times 10 to the power of 8 meters per second. Now remember that it's in meters per second, so we're going to have to convert any other units that involve distance to meters as well. We also have the distance that we mentioned earlier, 150.38 million kilometers. We're going to have to convert this into meters. So this converted into meters will be 150.38 times 10 to the power of 9 meters, because we are converting first the million phrase to scientific notation, which is 10 to the power of 6, and then we are converting the kilometers to meters, and there are obviously 1,000 meters in a kilometer, so it's another 10 to the 3, which gives us 150.38 times 10 to the 9 meters. Now we're looking for the time, so we're going to have to use our formula. We know that speed is equal to distance over time. So to begin, we need to fill in the variables we do have and then rearrange the formula to be able to get what we need. So the speed is 3 times 10 to the power of 8 meters per second. And this will be equal to our 150.38 times 10 to the power of 9 meters, all divided by our time value, t, that we need. So to get the answer, we're going to multiply both sides of the equation by t, and then divide both sides of the equation by the speed of light. This will give us that t is equal to 150.38 times 10 to the power of 9, must still include our scientific notation in the calculation, divided by 3 times 10 to the power of 8. So, definitely can't do that in our head. So to the calculator we go. We have 150.38. Forgot my brackets. Let's put the brackets in there. 150.38 times 10 to the power of 9, all divided by 3 times 10 to the power of 8, close the bracket, hit equals, and then convert it, we get that our time value is approximately 501 seconds. 501 seconds? That doesn't seem that much, or does it? I suppose if you think about the distance that we're talking about here, literally millions of kilometers, then that time doesn't seem that bad, does it? Can we expand on this idea? Let's have a look. If the time is only 501 seconds to travel that huge distance, how much is that in minutes? Well, that means if we convert 501 seconds to minutes, we get that this is approximately 8.3 minutes. i.e., it takes light approximately 8.3 minutes to get from the sun to us. We often refer to this unit just as that, a light minute, the distance that light travels in a single minute. It's quite a distance, but we use it a lot in physics. A term you may have heard used more in physics is perhaps a light year. Have you heard of a light year before? When people talk about light years in movies, do they usually refer to a period of time or a distance? Well, you'll often find that if the movie was made by someone who understands science, light year will be used correctly to describe a very large distance, i.e. the distance that light would travel in a single year. If they're not very clued up on science, they tend to use the term light year to describe an amount of time, which it is not. And so that's a nice example of how some people who don't understand science as well as we do tend to make silly mistakes in their use of the terminology. This term, a light year, how far is that distance? Can we do that calculation as well? Absolutely we can. Let's have a look. So we already know that light travels at 3 times 10 to the power of 8 meters per second in a vacuum. And with a quick bit of math, I was able to determine that there are 3.154 times 10 to the 7 seconds in a single year. Therefore, if we use our formula, but just rearranged from the previous slide, we can get that distance is equal to speed multiplied by time. And when we multiply the speed of light by the number of seconds in a year, we get that the distance of a single light year is 9.461 times 10 to the power of 15 meters. A truly colossal distance. Far, far longer a distance than the distance between our Earth and the Sun. All right, so now we've come to the end of the section. Let's take a short break, and when we come back, we can have a look at how electromagnetic waves propagate through space. Welcome back from that short break. Now it's time to have a look at how electromagnetic waves travel through or not through a medium. Let's jump back onto our concept map to remind ourselves of what we've been talking about. We've already related the behavior of waves to electromagnetic phenomenon, and we've looked at the behavior of particles and tried our best to relate it to electromagnetic phenomenon. We related the uniqueness of the speed of electromagnetic radiation. Now it's time to understand how it propagates. Have you ever seen light being made? Have you ever seen any kind of electromagnetic radiation being made? The answer is no, not at least with your naked eye. So how does it form and how does it propagate? Let's have a look. For us to understand how it propagates, we first need to know what propagate means. Propagation is the spreading out or the dispersal of something. Now, if you've ever turned on a light in a room next to your room and left your room in darkness, you've been able to see how light propagates out of the lit room into the adjacent room. The next key word we need to familiarize ourselves with is that of a field. Now, in physics, a field is not something that we play sport on. It is in fact a region in space where objects experience forces. You may have examined or heard about fields before. Can you think of any examples of fields that we've worked with already, or perhaps fields that you've heard of mentioned? We often in movies talk about an electric field. Do you think that there's an electric field involved in electromagnetic radiation? I certainly hope so. Let's have a look at fields in a little bit more detail. We said that a field was a region in space where an object experienced a force. We get different types of fields, and the first one we're going to be looking at is an electric field. Electric fields are usually given the symbol E, and they are simply a region in space where a charged object will experience a force. All right? A region where charged objects enter the space and then experience a force. Have you ever experienced electric fields in your own life? You probably have without ever realizing it. Have you ever had a blanket and run it over your head and then had all your hairs stand up? Maybe you've seen in movies or on TV when people touch the dome of a Van de Graaff generator, their hair stands up. Or someone who's been electrocuted in a cartoon has all of their hair standing on end. The reason that the hair stands on end is because electric fields are generated around each individual hair that repel one another, causing them to stand up and as far away from each other as possible. Another type of common field that we need to examine is magnetic fields. Now, you experience them in your everyday life as well, but perhaps you don't know all that you should know about them. Let's have a look. So magnetic fields are, again, just a type of field, and they are given the symbol B. In fact, sometimes they're affectionately referred to as B fields. A magnetic field is simply, again, a field, which is a region in space, but a magnetic field specifically is the type of field that forms around magnetic objects. When another magnet or object made of a material that is considered magnetic enters this space, this field, it then experiences a force. Now, the magnetic fields that you and I experience in our everyday lives are not quite like the ones that we're going to be looking at in terms of electromagnetic radiation. They tend to be much bigger and quite a bit stronger. And usually when you and I think of magnetic fields, we think of simple fridge magnets, or maybe even electromagnets like you see used to pick up scrap cars in a junkyard. But the question is, how do electric fields and magnetic fields relate to one another, and how do they work together to allow electromagnetic radiation to propagate from one place to another? Well, let's have a look. I often encourage my learners when working with complex terms like electromagnetic to break the words up into components. Sorry, the slide's gone the wrong way. Just get the pen active. To break the word into components. Two obvious components here are electro and magnetic. Now, the electro part of the phrase refers specifically to the electric component of the wave. All right? And this is related to a changing electric field, i.e., when we talk about electromagnetic waves, we are literally in part talking about an electric field that is itself changing. The word magnetic again refers to the magnetic component of the wave. This is related again to a changing magnetic field. Now, this all might seem a little bit disconnected right now, i.e., how does an electric charge or the moving of an electric charge to make a field cause a magnetic field to occur? What kind of relationship exists between the two? How can we use them or relate them so that we can understand electromagnetic, the combination of the two, and how it propagates? When posed with such a complex word like electromagnetic, I often encourage my learners to break the word up to better understand each component one at a time. In the phrase electromagnetic waves, we have electro, which refers to the electric component of the wave, and it is related to a changing electric field, i.e., electromagnetic waves are in part made up by a changing electric field. The second word, magnetic, again in the same vein, refers to the magnetic component of the wave. And again, it relates how a part of the wave, a component of the wave, is made up of a changing magnetic field. But where do these electromagnetic waves originate from? Well, they originate from an accelerating charge. Now, in our investigation of the realms of physics and chemistry, we've only seen two types of charged particles: protons, which have a positive charge, and electrons, which have a negative charge. Now, you can imagine that getting to a proton trapped inside a nucleus can be quite difficult. So when we look at the propagation of electromagnetic radiation, we focus quite a lot on the role played by the electron. The electron, a negative charge that accelerates, is what causes or generates most of the electromagnetic radiation we have discussed or had a look at in these last few lessons. So let's have a look. When electrons are accelerated, they generate a moving or changing electric field. When this electric field is generated and moves, it is able to cause a magnetic field to be generated as well. I.e., if you ever move a charged object, you immediately induce a magnetic field at 90 degrees to the electric field associated with that charged object. And to help us visualize how these two electromagnetic waves appear, you can imagine the changes in each field as transverse waves. Now, this is all well and good, but how is the nature of the fields being generated by moving charges and them generating magnetic fields in turn able to propagate an electromagnetic wave through space and potentially time? Let's have a look. I've got an animation that should prove quite helpful. So in this animation, you can see that we have an electric field marked in blue and given the symbol E, and a magnetic field in red marked with the symbol B. And as you can see, as each field is generated, a complementary field at 90 degrees is also generated of the opposite type. So to put this into words, we say that each new electric wave generates a magnetic wave that then repropagates an electric field. The electric and magnetic fields induce one another, i.e., they cause one another to occur. And it is this repeating pattern that we consider to be electromagnetic radiation. This induction is self-propagating, which means that electromagnetic radiation does not require a constant source of energy. And this is also why electromagnetic radiation can travel without a medium, because an electric field and a magnetic field do not require a medium. All right, so now we've come to the end of our introduction to electromagnetic radiation and the electromagnetic spectrum. I hope you've enjoyed it and found it interesting, and I'll see you next time.